surfactant action in this case. You have those, you can buy them from different types of Photoshops and so on. It's car treatment for car windows. And it's essentially a surfactant which absorbs and hydrophobizes the car windows. So give it a try, and it's also good exercise in colloidal science. And in order to understand how surfactant hydrophobizes windows and so on, we're going to have to listen to that. You have to listen to that lecture. Now, this time it wasn't that difficult to find something beautiful and unusual. Now, what is this? Looks like a flower, but even if it was published in Science 3 years ago, that should be something scientific. Okay, we're going to find the answer to this one a little bit later in the lecture. Just keep this in mind. It's an unusual. Well, crystal, perhaps, but have you seen a crystal crystallizing in this direction? And then why people would publish a crystal in Science? People know how crystals look like. Let's come to this a little bit later in the lecture when we think about self-assembled monolayers. Now, this time this is shown properly, so that's how it should have looked the previous time. In the previous lecture we studied what happens when we have surfactant monomers in equilibrium with surfactant micelles. And then we studied equilibrium between surfactant micelles and different types of more complex self-assembled structures. So right now we know what happens in solution. We know why micelles form, we know why surfactant forms different types of spherical, planar, and different types of other structures. Now what we're going to study in this lecture is what happens when we have surfaces. And usually you put surfactant for some specific surface functionalization, like we discussed this solution for application on car windows. Now what happens when the surfactant reaches surfaces? It can be an air-liquid surface or liquid-solid surface. It makes a bit of difference in terms of theoretical description and in terms of applications. So we're going to go through these details now in this lecture. Now, let's start with something that is theoretically very fundamental and in a way simple once you understand it. Now, all of you have heard the concept of adsorption. So you know what adsorption is. Now, how do you define adsorption from the viewpoint of molecular thermodynamics? Now, this is an area where a big contribution has been done by Willard Gibbs, a name which you know from thermodynamics. Just as an interesting side step away from that, I was giving an invited seminar in Yale a couple of months ago, and Gibbs has worked in Yale, if you know. So I rushed to his graveyard, to his tomb, and I saw it, but my friend who took a picture didn't send me the picture, so I can't show you the grave, his tomb in the graveyard in Yale, but certainly we're going to study the theory that he has developed. Now, Daniel there had a question.
Well, we don't have the slides on the other monitor.
Hey, Chico, could you turn on the slides to the other monitors? Okay, thanks. So right now the question is now how exactly do we define adsorption? If we take a look, we're going to say, well, I mean, you know, this is the surfactant, whatever substance absorbing on the interface. It's at the interface, so, I mean, that's what it is. But then if we take a look on a molecular scale, you have the liquid here. The liquid is dense. As we discussed already, the liquid molecules don't jump on a, let's say, atomic scale. They don't become a gas instantly. There is this transition region. And then you're going to have these molecules of surfactant or whatever close to the interface. Now, there would be an increased concentration on the interface, but again, this is not a layer which is exactly well defined. You may have some increased concentration further down in solution. And then you have surfactant in solution. So the question is how exactly you define the adsorption. Same is the case when we have solid surfaces. The surfactant may be here on the surface, but it's going to also be in solution. And thermodynamically, how are we going to define exactly the amount of substance that is dissolved there? And we need this because adsorption thermodynamics essentially deals with interfaces. So it's a two-dimensional thermodynamics. Kind of, you think of the surfactant being in some certain plane here. So adsorption is essentially gives you the excess of the surfactant which is ascribed to this plane. So what we're going to think about, I'm going to define a plane here, and everything that's in excess to the bulk properties is going to be confined in this plane, and I'm going to develop the thermodynamics of this two-dimensional system. So the thing that Gibbs has essentially proposed is to develop this surface excess concept. So you assume that the bulk concentration of substance is constant until the interface. Then you assume that you may have some, if it's volatile, you may have some in the gas phase. You assume that again, whatever is in the gas phase is constant up to the interface. So there is a sharp jump between this one and that one. And then you have some, in the real system, you're going to have some additional amount of substance here. So what you see here is concentration of surfactant as a function of the distance across the interface. So the surfactant, or whatever adsorbs, is going to be uniform up to here. Then it's going to have a region of increased concentration. What you do is you assume that its concentration is like that, and all the rest is ascribed to the interface. It's a excess concentration at the interface. And in order to calculate that, you need the total number of molecules in the system minus the volume times the concentration in the liquid phase minus the volume times the concentration in the bulk phase. So the total amount of moles minus the moles in both phases gives you the excess moles, which should be on the interface. Now, then the adsorption, as of course, it should not be extensive quantity because you want it to be a characteristic of any system. So then you have to divide by the surface. So you have amount of number of moles per unit area is equal to the excess molecules per unit area, what is commonly denoted as adsorption. Thermodynamically, this is the definition for adsorption. And now we have to define this for any component in the system. We cannot say we're going to work only with surfactant, because for full thermodynamic descriptions, you cannot say I'm going to describe only this component and neglect the rest. So in principle, we have considered the adsorption of all species in the system, including the water for example, which is the solvent. And now I'm sure that you're going to love this slide, but you have to follow. Here it's very simple, thermodynamics. Now we want to develop the thermodynamics for this interface. And to work in a system which is isolated, you control the surface area and you control the number of moles inside the system. So we work with the internal energy of the system. This is the common differential expression for the internal energy, including the surface. Now you know this term already. This is the one that comes from the surface tension. And it is the one which is going to give us interesting things. Now, you can write the integral expression for the surface energy, which is going to be the same terms, but without the differentials. Now, the differential of the full expression is equal to podos like T times delta A, T times ds plus S times dt, gamma times dA plus A times d gamma, and so on. So the differential is the full differential is the sum of the differentials of all variables. Now, we can subtract this expression, which is let's say, the differential of what matters, from this expression, which is the differential of everything. And we have this expression, which tells us that these three terms, actually this is a sum of terms, equals 0. The entropy, the surface entropy times the temperature, plus the surface area times the interfacial, the differential in the interfacial tension, plus the sum of all moles, excess moles of surfactant or whatever on the surface, times the differential of their chemical potential is equal to 0. Now again, pay attention that all of this is to the surface, not to the whole system. This is what concerns the surface. And you know this expression because this is the equivalent, you remember from thermodynamics, Gibbs-Duhem equation, which relates the differentials which in any systems, when summed up, equal 0. So all I have done here is derive the Gibbs-Duhem equation for the surface. And then we can rearrange this equation. You see that we have A here. If we divide the number of moles by the surface area, we're going to get adsorption. This one here. We take out the gamma from on the other side. And simplifying this, now let's think a very simple system, water and surfactant and water vapor after the above the interface. We arrived at this equation which tells us that the differential of the interfacial tension is going to be equal to the differential of the absorption of the first component, which is water, and the differential of the absorption of the second component times the chemical potential. So the change in the surface tension will be equal to the change in the chemical potential of water times the absorption of water, adsorption, because water is a component, plus the adsorption of the surfactant times the change in the chemical potential of the surfactant. Now we have to get rid of something here, which is the water. But before that, any questions about this thermodynamic derivation so far? All of you are familiar with the Gibbs-Duhem equation, I hope. So this is just Gibbs-Duhem equation for surface. Rewritten in terms of interfacial tension, adsorption, and chemical potential. We have dropped also this term because you work at constant temperature in a closed system, so we don't care about entropy and temperature. Now, just in terms of terminology, the fact that we dropped this term is reflected where? In what name? Isotherm, right. So that's why whatever we're deriving here is going to be called surfactant adsorption isotherm or interfacial tension isotherm, because like isotherm actually means that we work at constant temperature. So it does not mean a relation or something like that, it just means it's constant temperature. What we mean by surfactant adsorption isotherm is the relation between the moles of surfactant on the surface and the moles of surfactant in the bulk, for example. What we mean by interfacial tension isotherm is the relation between the interfacial tension and the moles of surfactant in the bulk. Okay, so we have arrived at this expression. It's not exactly what we like. We have to go a little bit further here. Just one more slide with thermodynamic expressions and definitions. I have started with the previous expression. I have rewritten it here just for being immediately understandable. What we have here, gamma of water, dmu of water, gamma of the surface, dmu of the surface. Now this is the second component, which is S is for surfactant. So it's not for surface. I mean, like gamma S would be, everything is on the surface, but this is a surfactant. So right now you know kind of intuitively that water does not adsorb at the water interface, right? But actually this is not quite true if you just think of thermodynamics definition. It depends on where you're going to define the interfacial boundary, where you're going to define the surface. Let me give you an example of that. Okay, this smiley face here would now imagine you have a water droplet. In thermodynamics, you will say, I don't care where the real surface of the droplet is. I'm going to define the surface of the droplet to be here, inside the droplet, not on the actual interface. Now, what is going to happen then if you try to calculate the adsorption of water? If you remember, adsorption means that the concentration until up to here is equal to the bulk concentration, and the concentration up to here is equal to the vapor concentration. But you have some additional, you did not define the interface to be coincide with the interface of the droplet. So all of this volume actually has to be ascribed to the surface that is going to appear as adsorption. So if you define thermodynamically the surface of the droplet to be different than the prior radius of the droplet, you're going to get adsorption of water. And of course you don't want to do that. So you just have to define the right interface in order to get rid of the adsorption of water. And the way you defined it, you're going to say like that. Now let's say this is the concentration of water, the real concentration of water through the system. And I'm going to think that I'm going to put in the dividing interface here. So this deviation is equal to this deviation. So there is no, if I assume that the ideal interface goes like that, there is no adsorption. What is in excess here on that side of the interface is equal to the smaller volume or to the decreased density here on the other side of the interface. So even though water-air interface may be a bit fuzzy, you say this is the interface. If I had a very straight molecularly smooth interface without any change in density, this is going to be the interface where the water would not have adsorption as defined thermodynamically. Now we cannot define such an interface, at least not in this area, for the surfactant. When we define the interface of water to be here, it's going to go through the highest concentration of surfactant. There would be excess concentration of surfactant both here and here on both sides of the interface. So the surfactant is always going to have adsorption of that interface, but this term can be happily neglected. And then we arrive at this formula here where I have put up the smiley face, which is the formula which is very simple. It tells you that the adsorption of the surfactant on the interface is equal to the derivative of the interfacial tension with respect to the chemical potential. It looks beautifully simple. Now what is the problem with this formula if you want to use it practically? The problem is that you don't have in your laboratory an apparatus which is going to measure chemical potential. So unless somebody develops a chemical potentiometer, we have to express it with something that we measure experimentally. And in order to do that, we take the common expression for the chemical potential. You know it, the chemical potential is equal to the standard chemical potential plus RT logarithm of the concentration. We don't know this, the standard chemical potential, but we don't care about it either because we have a differential here. So we need to take the differential of the chemical potential, which is equal in this case only to this term, RT, the differential of logarithm of the concentration. Then we substitute this in this beautiful expression here. It stops looking that simple of only three quantities anymore. But it's still simple enough and it's very important. I mean, this is a beautiful expression which tells you everything you need to know about surfactant adsorption at liquid interfaces. It tells you that the adsorption of the surfactant on the interface is equal to this constant, which depends on the temperature, the differential of the surface tension over the logarithm of the concentration. So we have an expression which links gamma, C, and interfacial tension. You have an expression which links all the three parameters which you need to know about the surfactant. You want to know what's the bulk concentration, you want to know how much it adsorbs on the surface, and you want to know what happened when it adsorbed on the surface, how much did it change the interfacial tension. And this is the Gibbs adsorption isotherm, the practical form, which is really important, and you can use it in your practice if you happen to work with surfactant solutions and interfaces and so on. Okay, a small break here, time for questions. Okay, so I assume that then you have followed everything up to here. We know this isotherm. Now, of course, we want to see how we use it in practice. These are actual experimental data for the interfacial tension of a variety of alcohols, C6OH, C7OH, up to C10OH. Now, alcohols are not very strong surface active agents, so sometimes you need to go to high concentrations, but on the other hand, they have very simple molecular interactions, so they follow the thermodynamics very well. Now, what we have here is the interfacial tension, which you can measure with what? Wilhelmine plate, or shape of droplets, or weight of droplets, and so on. You remember this part of the lecture, as a function of the logarithm of the concentration of the surfactant. Obviously, it's not plotted here, but obviously, when you have zero surfactant, it will go, now this is a logarithmic scale, so it cannot go to zero, but at a smaller concentration, all of those interfacial tensions are going to go towards the interfacial tension of water, which is 72.8. At higher concentration, the interfacial tension starts decreasing. And you can see that in almost all of the cases, it decreases linearly. Why does it decrease linearly? Because the Gibbs isotherm predicts that the slope of the interfacial tension over the logarithm of the concentration should be linear. Now, this is the kind of the who thinks faster question. Now, which of those is C6 and which of those is C10? This is C6, C7, C8, C9, and C10. Now, which is which? I have deleted this here, so you have to tell me.
C10's on the left and C6 is on the right.
Okay, good. That's okay. So you win the prize for fastest answer here. True. And why is that?
Most oil-like.
Right, which means also what?
Lowest surface tension.
Right. It's kind of, this surfactant would be the strongest in terms of it has the longest hydrophobic chain. Strong surfactant, kind of strong, means that when you put a small amount of surfactant, it's going to decrease the interfacial tension fast. So that's why this surfactant starts working at lower concentration than the other ones. You can actually see how kind of the strength of the surfactant influences the interfacial tension. If you're designing an industrial product, let's say you want to have this has to be the interfacial tension of the product. You can just put in this much surfactant C10, then you have to put 10 times more C8 and even more than 10 times more C6 if you have to achieve the same result. Now, this was one question. Now, the second question is, what happens when you extrapolate those curves here? Where do they go?
Level off.
Yeah, okay, this is an obvious question for everybody who knows a little bit about colloids. And they level off because of? Right. So eventually, let's say this is going to be the critical micellar concentration. The interfacial tension decreases. You reach the critical micellization concentration, and then it levels off because the chemical potential of the monomers remains constant. The concentration is constant. The chemical potential is constant. You have here the concentration of the monomers. The concentration of micelles does not matter, at least on this simple theoretical scale. So it levels off at the CMC and then stays more or less constant. Now time for questions, but I have one more question actually. Again, like if somebody has read the books, he can tell me. Otherwise, it would be a good just hint for you if you decide to study surfactants at some point. Now you buy SDS, sodium dodecyl sulfate, and you decide to kind of check out whether Gibbs was right and put SDS in water. Now you assume that when you buy it, it's nice, good, surfactant and so on. You start dissolving it in water, a different concentration. You measure the interfacial tension and you make the interfacial tension isotherm, like that. And then what you find out in practice, in many cases, would be that the actual curve would go something like that. So it goes down faster. It actually dips just below CMC and then it goes up again a little bit and levels off. Now, I mean, you can try giving me an answer. I would be suspicious that you can immediately think of the reason for that, but I mean, you can have a try for that behavior. Why would that happen? Now, I mean, I have to tell you immediately that you don't have to try to find your own interfacial tension isotherm and correct Gibbs, because this is not a fundamentally important behavior. It comes from some practical, let's say, hitch. What might happen here? Okay, let me tell you the answer. Now, for example, SDS is sulfate, but it hydrolyzes. So you're going to have a mixture of, like, I mean, even if you buy very clean SDS, you're going to buy a mixture of sodium dodecyl sulfate and a little bit of alcohol, decyl alcohol. Now, decyl alcohol is very active and it mixes with SDS to decrease the interfacial tension. So when you start adding the surfactant high concentration, the decyl alcohol is actually going to decrease the interfacial tension. The dodecyl alcohol is going to increase the interfacial tension further. So you are actually going to measure interfacial tension which is lower than the one of pure SDS. Now then, what happens here? Why does it level off at higher concentration? It's a small amount, right, but it's still on it was at the interface when you reach CMC. What happened afterwards?
Oh, it's in the micelle.
Right, yeah, it got solubilized. You remember the 10 micelles can solubilize additional hydrophobic components and so on. So because you put in so much micelles here at higher concentration, they solubilize the impurity from the surface. So you eventually get to have a clean surface here, high above CMC. This is a known artifact, and quite a few people have considered they have made a fundamental discovery, but I mean, like they were wrong, obviously. Even these days this happens at conferences. I have heard of similar occasions where people report some very exciting discovery about SDS, and I mean, somebody just asks them, did you purify them from the alcohol? Then there is what alcohol and all unpleasant consequences for the speakers. Now, just one more thing to note here. Now, the actual adsorption would be the derivative of the slope. So it would look like that. Okay. These derivatives are going to be almost the same, but this one is going to be actually, I put it quite high slope. You can see that actually the slope slightly decreases in this transition from C10 to C6. I'm just going to put 6 here. The reason for that is, well, the reason is because you have lower surfactant activity. The adsorption is not that high. But in practice, if you have to measure the adsorption, you have to take the derivative of these lines with respect to the concentration. Okay, so much about Gibbs adsorption isotherm. Any questions, comments? This is something that's very important for you to know. I mean, this is the basics of surfactant, so just make sure that you understand all the details well.
So do you take it as a limit to the point where it goes to CMC?
Well, if you want to, you take it as the derivative at the point where you want to measure the adsorption. If you want to measure the adsorption at this point, you're going to take the derivative here. If you want to measure the adsorption at CMC, which is the limit adsorption, the highest adsorption, you have to take the derivative at the CMC. Being careful about the artifacts which occur around the CMC point.
I have a question.
Uh-huh.
You said earlier that they were almost linear. Are they supposed to be linear?
They are supposed to be linear if you follow Gibbs isotherm, right?
Okay,
So why they are not?
well, if the points don't have to necessarily be linear, but the curves that fit them should be, right?
Well, on a certain scale, they are linear. Now, they have this general curvature, which comes because Gibbs adsorption isotherm is, of course, an idealization of the system. And you can see that actually it starts working poorly here at low concentration, just because you have very little surfactants, they can adopt different configurations and so on, so it stops being described well by the Gibbs adsorption isotherm. But on the other hand, on the experimental scale that you would typically encounter if you don't work specifically in this area, you can see that if you take certain region, they are fairly linear. I mean, you can take the derivative and you can measure the adsorption. But of course, all this is the idealization. Now the question is, what happens if you have to measure this very precisely and you have to describe it exactly by theory? And the answer is that people have worked after Gibbs and they have developed different types of isotherms, Shishkovsky, whatever isotherms and so on. So similarly to the corrections to the van der Waals law, you have more and more complex behaviors. So depending on the complexity that you need, you can always find some isotherm which is going to describe your data precisely enough. But the point about Gibbs isotherm is that it works while beautifully explaining the physics of what happens in the system. The relation between chemical potential, surface tension, and adsorption. Let's move on to adsorption at solid surfaces. Now, why is the Gibbs adsorption isotherm not good for solid surfaces? When we derived it, we didn't really have a problem. Thermodynamics doesn't distinguish between solids and liquids and gases. So why is the Gibbs adsorption isotherm not good for solid surfaces?
They can't deform.
Well, we don't have deformation here, do you? But, I mean, you're on the right track. The reason is that we have here this parameter interfacial tension, which, if you remember, for solid surfaces is theoretical rather than experimental. You can't measure interfacial tension of solid surfaces. So just trying to find the relation between interfacial tension of solids and concentration of surfactant it has no practical meaning. And it cannot be experimentally confirmed. So then you have to just think how you can describe adsorption on solid surfaces. And people have done this a long time ago. Langmuir has just described a very simple scheme for essentially thermodynamic equilibrium between adsorbed amount of surfactant or whatever in the surface and in the bulk. And now you need here in this case you need some equivalent of surface concentration. And again, it's difficult to define it because you don't have gamma. So the parameter that is used is degree of coverage. So you can assume that the molecules are, let's say, spheres or whatever size. They each occupies a certain area. And you can only put this much on the surface because before you cover it, all of it. This would be the maximal adsorption on the surface. So then you can normalize the adsorption at a certain concentration with the maximal absorption. And you have this parameter theta, which varies between 0 and 1, which gives you the number of surface sites which are occupied versus the total number of sites. Total number of sites means the total number of molecules which you can absorb on the surface. So we have this parameter. Now, in equilibrium, the rate of adsorption is going to be equal to the rate of desorption. This is just chemical kinetics. The rate of adsorption would depend on two parameters. Now, it would depend on how many molecules you have here, because the more molecules you have in the bulk, the more molecules would tend to adsorb toward the surface. It's going to also depend on how many molecules you have on the surface, because in order for these molecules to adsorb, you have to have free surface area, otherwise they cannot adsorb. So the rate of adsorption would be the absorption constant times the concentration in the bulk times 1 minus the occupied sites on the surface. So this is essentially free surface area. Now when you have desorption, however, you have high concentration of material on the surface, you have low concentration here. So the fact that you have some molecules here would not be a problem for a molecule which wants to get away from the surface. So the molecules on the surface don't care how much surfactant you have in the solution, because you have little surfactant enough, so it does not make a barrier for desorption. So that's why the rate of desorption is equal to the desorption constant times the surface coverage. In equilibrium, of course, these two will be equal. So when you equalize them and when you rewrite the expression, you obtain the Langmuir adsorption isotherm, and you don't know the rate of adsorption and the rate of desorption. So what you can do is you can bundle them in a constant, which just gives you the ratio of adsorption rate over desorption rate. So the Gibbs adsorption isotherm tells you the relation between surface coverage and surfactant or whatever concentration in the bulk, and this constant, which is effectively the coefficient which tells you how much the surfactant wants to adsorb. The higher the constant, the higher the propensity, the desire of the surfactant or whatever to adsorb on the surface, because the adsorption rate will be higher than the desorption rate. And this is an example of how it works, and you can ask questions if you have any. When you plot that, you want to plot something in terms of gamma, which you can measure eventually experimentally. So a more convenient form, which people usually use, is this one. You have a slope which is going to give the constant, the Langmuir constant. You have the intercept, which is going to be equal to the maximum absorption. So when you measure gamma and C experimentally, if you plot them in this scale, you are going to obtain gamma maximal and the Langmuir constant from the slope and from the intercept. And just to end up on that, one thing that is very common for Gibbs adsorption, for Langmuir adsorption isotherm, is that it's not valid only for surfactants. I think I've given you one question for homework. The same equation is also valid for adsorption from gas. So in this case, we're going to have, instead of concentration, we're going to have pressure. And this is a equation which is used very much, which is used in all types of, let's say, adsorption from gas, all types of industrial processes where we have to remove a certain component from a gas mixture and so on. Chemical protection, gear if you like, all of those essentially start with the Gibbs with the Langmuir adsorption isotherm. This is an example of how it works. At low constant K, you have to increase the pressure a lot in order to have some gas adsorbed. At higher K, you have the very high adsorption and it levels off very fast. This here is going to give you, this is your maximal adsorption. Now, know that in many cases, this here can be linearized, especially for small for small pressures, for example, or small concentration. And when it gets linearized, all we have here is essentially an equation which looks like that. The absorption is a linear function of the constant of absorption and the pressure or the concentration. This is used at low surfactant or low gas absorption and pressure. Yes, Chris?
How do you measure the coverage, like for?
There are a variety of methods. Now, the best, possibly the best one, and the one that's least used these days, is by radioactivity. If you take radioactive species and absorb them, then just by measuring the radioactivity, you can measure the amount of the absorbed substance. Now, obviously, for obvious reasons, this is not used that much these days. But you can measure capacitance. You can measure different types of infrared reflectance spectra, although surface spectroscopy techniques would eventually give you the amount of absorbed substance. So surface FTIR, for example, is one technique which you would use today, but the most precise one is radioactive activity, or at least historically. Same accounts for surfactant. How do you measure surfactant concentration on the surface? This is a non-trivial problem. And there are good methods to do that. Of course, you can use infrared and so on. One other method is to measure the surface potential and relate it to the degree of charging of the surfactant on the surface and then to the surfactant concentration. So there are methods for measuring absorption, but they are not that good. So that's why for surfactant you don't want to measure absorption. You want to measure interfacial tension and then calculate the absorption from the Gibbs isotherm, rather than trying to measure how much surfactant you have on the surface directly. Now there is also, of course, this day, if you think about something that gets to be of better importance, can you see the molecules on the surface directly and count the number of molecules per surface area? What is the technique that allows you to do that? Right, yeah. I mean, yeah, FM would be better. I mean, like STM is, I mean, yeah, STM is true, but FM is better. I mean, these days, people would, for large molecules, for biological molecules, people would count directly the number of molecules on the surface per unit area. Okay, and going towards the second part of the lecture today, where we don't have so much formulas, but we have lots of important applications. Now, what we discuss here is really the basic fundamentals of colloidal science. But it has not much application in nanoscale engineering these days. And the reason is that it's not exactly absorption, desorption, mobility of surfactants is not exactly something that you can use to design something on a molecular scale. If your something absorbs and desorbs and so on, it's not really design, right? So the real way people do molecular type of engineering and colloidal engineering is by using what's called insoluble surfactants. And I'm certain that all of you have heard about self-assembled monolayers or Langmuir-Borget monolayers and so on. So let's go through this in the second part of this lecture. Now, I'm going to terminologically distinguish two types of layers. Some people would try to bundle everything into self-assembled monolayers, but I don't find this to be true. From my viewpoint, the self-assembled monolayers are only monolayers which form at solid interfaces. As we're going to see at liquid interfaces, we have molecular organization of the surfactant, but this is not a self-assembled because we control the surface pressure, which we're going to study right now. So if you compress something, I mean, you don't say that it's self-assembled because you compressed it, right? Now, Langmuir-Borget films and layers are one of the longest studied colloidal topics, and these days they are finding again very important applications because again of nanoscale processes, nanoscale functionalization and so on. We're going to discuss a few applications by the end and so on. Now, why do you call this insoluble surfactants? Because In the case on the surface, you would like surfactants which absorb so strongly that they're going to stay nowhere but on the surface. They are not going to go into the liquid at all, they're going to stay on the surface and only on the surface. So essentially all the molecules are there. And you know one simple substance like that, you can study it in your soup actually. This is lipids. If you you have noticed what happens when you drop a lipid droplet on a surface. It spreads out, but it's not going to penetrate the bulk of the liquid, right? Lipids don't dissolve in water. So lipids would be typical, but these days people design special molecules which have special properties. And if it's on the surface, it's still not colloidal engineering because it's kind of too fluid. So we're going to discuss also how this can be transferred onto solid surfaces. And then there are molecules of surfactant which would go absorb and directly form monolayers on solid surfaces. I wouldn't call these surfactants insoluble because in order to go to the solid surface, they have to be soluble in water, for example, or whatever, right? So the reason these surfactants absorb on solid surfaces is because they have strong absorption on the solid surface. In this line, the term insoluble is not quite true. You can think of surfactants with very strong absorption, which may eventually be insoluble. And we have to give due here to the people who have developed this. Now, who is Langmuir-Blodgett? Okay, a scientist? Is it a scientist or not?
It's more than one. Two.
Yeah, that's true. I mean, Langmuir, now there are two researchers who worked for General Electric in the beginning of the previous century already, and developed most of the modern colloidal science. Blodgett was actually a female and one of the first well-known females in colloidal science. She was very famous for her time. They worked together to develop the Langmuir-Blodgett techniques. And the first thing that they actually designed was a way in order to study these surfactants. You want to be able to measure something, right? And you want to be able to compress them eventually. So, okay. So, you have a two-dimensional system, so you have to design a two-dimensional way to move the surfactants two-dimensionally. So what they did was eventually put a barrier on the surface, which these days is typically a piece of Teflon rod, square Teflon rod. When you move the Teflon across the surface, the liquid can go below the Teflon, but the surfactants cannot jump over through the air or cannot go through the liquid. So the insoluble surfactant can be compressed by using the Teflon barrier. So you can compress it to a monolayer here, nothing on the other side. Now, the way this works is you have this barrier which moves by two screws parallel to the surface. You have actually a pressure meter, the equivalent of really two-dimensional pressure, which can be just a balance, a small barrier which is equilibrated by a balance. Now, this barrier would of course have it has thin fibers here which do not allow the surfactant to go around. So this is the one you measure the pressure. You can measure the interfacial tension by Wilhelmy plate, which is usually also present in Langmuir-Blodgett balances. And the final experimental problem that you have is that if you drop let's say your lipid as a small chunk of lipid, I mean it may not spread fast and even and so on. So that for this reason you take the surfactant, dissolve it in volatile solvent, drop a droplet of the solvent on the surface, the solvent evaporates, the surfactant spreads out, and you have this monolayer which you can compress with the barriers, and which you can transfer to solid surfaces, as we're going to discuss a little bit later on. And of course, you still need to the quantitative parameters here. What do you use to estimate the surfactant properties? Now, why is this called the pressure? I mean, it's a little bit counterintuitive. If you think when you have surfactant, actually it decreases the interfacial tension. Why would then the presence of surfactant be considered the equivalent of a pressure in 2 dimensions? Actually, you can see this from this is gamma, and this is gamma 0 here. What happens is you have the barrier. The interfacial tension of this side would be higher or lower? Lower, because you have surfactant on the surface. This interfacial tension is going to be higher. Then if you take the difference between this interfacial tension and this interfacial tension, the equivalent is going to be a force which acts in this direction on the barrier. So it's the equivalent of a 2-dimensional pressure which tries to push the barrier. And it's really a pressure. If you have something on the other side which can move, it's going to move. You can with the simplest experiment. Again, I was thinking that it would be good to show, but I didn't have the right. If you take the right materials, if you just take particles and put them on the surface and drop a droplet of lipid, you're going to see how the lipid is going to push the particles apart. So you can think of the lipid as a 2-dimensional fluid which spreads out and exerts pressure on the surroundings.
At some point it would form a micelle or no? Like you push it together too much or?
Good point. Good point. It doesn't form micelles, actually. It is the exact equivalent, 2-dimensional equivalent of a 3-dimensional phase. And I'm going to show it. It has gas phase, it has liquid phase, and it has solid phase. And the solid phase is the one which is important for nanoscience, by the way. But before we do that, if we have low concentration, you just have a 2-dimensional gas on the surface of the liquid, and you know what is the equation for the ideal equation for a gas. Now this is the same equation written in 2 dimensions. The 2-dimensional pressure times the area is equal to the number of moles times RT. So instead of volume times pressure equal to the number of moles, you have surface pressure times surface area equal to nRT. And again, when you work with surfactant, you want to work on a molecular basis. So if you divide this by the Avogadro number and by the number of surfactant molecules and so on, you can have this equation which tells you that the surface pressure times the area per single surfactant molecule is equal to kT. You remember the rule of thumb that I was telling you, that the constant K appears when you have molecules, the constant R appears when you have moles. So, and essentially this is most of the math, the theory that you have about surfactant monolayers, to be frank. So most of the important things there are experimental, and we're going to go through them a little bit later in the next few slides. Questions so far?
Can you control the space between the 2 molecules?
Yeah. That's why you have the barrier, right? You put the surfactant here, and then you have these 2 screws. The surfactant is here. So then you start moving them, so the whole barrier moves in this direction, for example. You're going to do what? You're going to compress the surfactant. It is the equivalent of the 2-dimensional equivalent of having a 3-dimensional piston and pushing gas. And it's a good question because it's a good introduction to my next slide. What happens when you have gas in a cylinder and you compress it? It gets to be liquid and then it gets to be solid. Same thing with surfactants on the surface. Now, the most common, now you should be kind of, again, this is something very important to remember from this lecture. The most common way of presentation of data from Langmuir, Borget monolayers and so on is this type PA isotherm. So this is two-dimensional pressure versus area per molecule. And then this is actual experimental data. What happens when you start compressing surfactant? Now you see the area per molecule. Now you have 10 times the area per molecule than a molecule would have in its normal state. And then you go down. Okay, 10 times, no, you don't know exactly how much. This would be the right time. It's actually more than 10 times. But the point is the molecules here are just gas, which, I mean, they are chains which stick into the air. The hydrophobic ones are out into the air, right? They can adopt any configuration. They can lie on the surface and so on. The molecules move around. They are gas. Then you go down. When you reach this point, what happens? The surface pressure remains constant because you have the formation of a liquid phase. So you eventually, you have liquid-gas equilibrium. The liquid phase would be something like here. The molecules are close together, but their chains still can kind of move around and so on. When you reach this compression point, all the molecules are compressed into liquid. You compress them further, and then you have, this is called second liquid phase, liquid condensed phase. This is a phase where the chains are more, kind of suddenly lose one more degree of freedom. This may happen with some surfactant, this may not, but this is the most complex one you can find. You can have two liquid phases just depending on how tight you pack them. Again, you have a liquid, this is essentially liquid-solid transition. So liquid 1, liquid 2 transition actually. You have this liquid condensed phase, and at some point you reach this phase and suddenly the pressure increases drastically. Now what happens here? Right. Right. I mean, you have a piston and you start compressing things, and you know at some point the pressure is going to jump very hard because you can't compress it anymore. You have reached crystals. So this is the exact equivalent of a solid phase. The surfactants here are tightly packed. All their chains stick out and they are ordered. So you have packed them in the tightest, smallest packing that you can obtain. Yes?
If you took the same amount that you had on the surface,
Uh-huh.
a cup that had that same surface area, instead of putting it, placing it on the top, you put it in the bottom of the cup and you let it rise to the surface, would it ever get to that solid phase over a long period of time?
Yes, sure, but I mean this is soluble surfactant, so it's difficult to put it in the bottom and let it rise, right?
Physically push it down there and let it.
What you can do is you can just drop it on the surface. It's going to spread out, but it's going to spread out to a crystal. It's going to be slow though. And because all those processes are slow and you have complex nucleation phenomena, this is actually the reason why we have these pictures that I showed in the first slide and so on. So you could actually follow the crystallization. Now, we're not going to discuss right now how, but you can follow the nucleation and crystallization of the surfactant on the surface. And the first image with the one that looks like a flower that I showed in the first slide is actually similar surfactant crystal in two-dimensional Langmuir-Bourget layer. It has important fundamental aspects, so that's why it's published in Science. But what you see is similar to this one. This is at different temperatures. You can see what happens. These nuclei, which are crystal here, become more and more liquid-like when you increase the temperatures. Now you can study surfactant monolayers by AFM2. You can deposit them on a solid surface and you can see them by AFM. Now the question is, how can you see this visually? I mean, does it look like a difficult problem or not? What is the length of a surfactant chain? Right. Yeah, a few nanometers at the most. So the point here is, and that's also what's interesting for nanoscience. So we have a thin film which is thick only a few nanometers. Now how do you see this film on the surface? I mean, it's so thin that it's essentially transparent, of course, and it has no thickness which you can measure and so on. You can measure the thickness by AFM if you deposit it. Now people have developed what's called Brewster angle microscopy. This is microscopy under special condition of in polarized light, where you have very strong sensitivity of the reflected light of the conditions, the refractive index on the surface. So only polarized light and only at some specific angle and so on allows you to actually see, visualize those domains here, those crystals that form in 3 dimensions on top of the surface. This is beautiful. It's not that practically important, of course, because if you think about nanoscience, you're thinking about applications. I mean, flowers are nice, but I mean, how can you make a device out of them? But this is very important in understanding the phenomena. Now, just kind of the control question here. Now we have this system, for example. Let's say this one. Now, where are we on the phase diagram here? Would be somewhere, where? It will be somewhere here, for example. Liquid, what? Sorry? Because we have, let's say, liquid gas equilibrium. Now, okay, that was, so let me explain again. Now you have gas here. You can press the gas until it starts condensing into liquid. The pressure then remains constant until you condense the gas fully into a liquid, and then you have transition to another liquid state. Now let's forget this other state, just concentrate on this part. Now in this region, what do we have here in this region? You have some of the gas being into, some of the surfactant being into liquid, some of it being into gas, right? You keep compressing it until all of it is converted into liquid. This is this case. In this case, it just starts liquefying. Between this point and this point, you have this case here where some of it is liquefied. So this is two-dimensional liquid droplet. This is essentially two-dimensional liquid droplet or crystal, depending on where you are. And this is gaseous surfactant around, which you don't see. Good that you ask these questions, actually, because I mean I can go back and tell. So don't hesitate to ask if you agree.
Oh, yeah.
Okay.
So the figures in the first row, lower temperature.
This is what happens when you increase the temperature. This is essentially crystal in equilibrium with gas, which can be another state. When you go to higher temperature, this becomes liquid. So these are liquid droplets. These are crystals in equilibrium with a gas on the surface.
Why can't we observe gas phase?
Because, well, I mean, maybe you can with some method, but the gas phase occupies the whole area, right? Because also now here what you have is the surfactant chain being packed and standing up. The surfactant, so in the liquid or solid phase, the chains are like that. You have here the heads.
What sort of image is that?
Huh?
What kind of image is that?
This one is Brewster angle and this one is AFM. And the gas around will be something like this. So the gas is isotropic, it's all around the surface and so on. This one has some optical anisotropy. See, you can think of this as just a very, very thin oil layer on top of the water. And this is what you observe by Brewster angle actually. So it's thin two-dimensional oil droplet. And this oil droplet is thin only a few nanometers. So in a way it's amazing that such nanometer scale phenomenon can be observed on a macroscopic scale so easily and can be used in a variety of applications. Ben had some.
Instead of increasing the temperature, can we observe this transition from gas to liquid by increasing the pressure?
Not really. This is, if you remember the phase diagram, for three-dimensional case, you have a certain temperature below which you have solid being in equilibrium with gas, right? So this is again in 3 dimensions. This is the equivalent of below the three-phase, the critical point, and above the point. Critical, I mean three-phase point in the phase diagram. So that's why this is essentially when you have low temperature, you have in 3 dimensions you have solid being in equilibrium with gas. When you increase the temperature, you have gas being in equilibrium with liquid and liquid being in equilibrium with solid. You remember that? Should I draw the diagram here? PT diagram. Or so it's exactly the same equivalent as 3-dimensional thermodynamic transitions.
Is there some sort of the equivalent of surface tension on like maybe a one-dimensional tension to the outside of those areas?
You have on the outside, it's essentially closed. You have the barriers.
I mean, on the outside of those structures, it seems to form like maximum surface area structures, at least the top left.
You mean in how they grow and so on?
Yeah.
This is kinetic problem. This is what's interesting, but it's a kinetic. It's the same way, like this is very similar to, for example, how you have snowflakes growing. It's just the snowflakes start growing and growing some fractal or whatever patterns. Just for kinetic reasons. In the same way you have crystallization in 2 dimensions, it still grows in some fractal pattern. So this is not thermodynamically it would form a crystal, but kinetically the crystal is actually resembles a snowflake. That's how it draws. And again, what we're interested in is this one. We're interested in the solid phase. Now we have just this monolayer. Can we use this monolayer for something, and how can we do that? And the way to do that is fairly simple. You can take a plate and just dip it through the monolayer. Or you can put it below the liquid and take it out. Eventually you may want to control to be always above the pressure. So you can put, let's say, something that has higher surface pressure than the substance that you're using. So this has the equivalent of a piston. Just keep it at constant pressure. And then this is a solid plate. You dip it down. You take a layer of surfactant together with your down. Then you pull it out. Then you take another layer of surfactant with you on the way out, if you take it out. If you don't want the second layer, you can keep it on the water, move and take it out from outside the surfactant area. Then you can dip the same plane again, and this is going to repeat itself. A second layer would form, and then a second layer on the way out. And you have a variety of, depending on how you dip it, you take it out, you can deposit the layers one way or another way. So you can deposit them like that, or you can deposit them like this. Or you can alternate them and you can deposit different surfactants and so on. So this is one of the most powerful ways of depositing thin molecular films on surfaces. And it works beautifully. You can deposit 50 layers if you like. And you're going to say, well, these 50 layers are going to be, let's say, 100 nanometers thick. So I'm going to deposit the 100 nanometers thick layer by dipping the plate 25 times into the surfactant layer. It's a very simple, very beautiful kind of experiment, and directly relating to nanoscience. This is the way to deposit thin films. So, just a little bit about self-assembled monolayers by direct adsorption on surfaces. Now, in this case, actually what happens is the surfactant absorbs on the surface and then builds up until it reaches solid state. So the only parameter that you can control here is temperature. And this is related to Bill's question. At low temperature you have a transition between vapor phase on the surface to solid. At high temperature you have a transition between vapor, liquid and solid, Liquid would be just this chains on the surface flipping around and so on. So it would be everything is straight, aligned, and crystalline. So it's a kind of like very simple method. The point is, which of those surfactants which would absorb so strongly on the surface that they wouldn't dissolve if they're soluble. And there is one, only one, and it is D1 system for making self-assembled monolayers on surfaces. And this is alkane thiols which absorb on those surfaces. So you have a surfactant with SH group. It's not something that you would put in your detergent, laundry detergent.
Sorry, Dr. Davis. The battery has gone out on that.
Is it? Let me take the. Okay, I'll take this microphone here.
Sorry about that.
Is it okay now? Can you hear me now? Okay, I assume
Is it turned on?
it should be. This one should be all turned on. Can you hear me now?
Yes, sir.
Okay. So I can't write on the board anymore. But the point is that sometimes people would even equilibrate this to a chemical reaction. Now this is a very controversial issue. Is this a chemical or a physical reaction? But the point is that the alkane thiols would absorb very strongly on the gold. They're going to form self-assembled layers. And these self-assembled layers are of molecular thickness. So you can have a variety of applications. Let's go through the applications, and this will be the final slide. You have one summary slide, but I won't go through it now. Now, you have the ability to deposit molecularly thin films on surfaces. Now, what you can use them for? The answer is for many things that relates to high technology. Now, you have contact angle modification. This is an example combined with patterning. Now, these are droplets on a surface, and you can see that they are sub of micrometer size. So if you put a monolayer and then pattern the monolayer in this way, you can make droplets. Stabilization of nanoparticle suspensions, as some people here know quite well. If you want to keep the nanoparticles stable in any environment, you want to attach a layer of surfactant around them. And this is a very strong way. Chemical protection, this is against corrosion and so on. Now, one interesting property is that you can modify the friction of the surfaces. And modification of the friction on a molecular scale is very useful these days in hard drives. Now, in hard drives, you want the head to be as close to the surface as possible, but you still want to have a thin layer which is going to act as a lubricant. So the best technology for hard drives these days is actually assembling a self-assembled monolayer of fluorinated surfactant on the surface of the hard drive. So the head actually rides on a lubricant layer. It doesn't touch it, but even if it touches, there is a lubricant layer which is only a few nanometers thick on the surface of the hard drive. So that's one of the good applications of self-assembled monolayers these days. We're going to discuss patterning a bit later in the class. If you put biocompatible monolayers, you can modify them so you can have cells, biological cells absorbing on the surface, photo and electrically sensitive surfaces, and finally, if you take special surfactants which have electronic properties, you can have molecular electronics devices. This is a very controversial issue, so I'm not going to go into molecular electronics here. It's not easy to make molecular electronics, but some people believe that one way to do that would be by using self-assembled monolayers. So this is the summary. You can read through that. So let's finish up this lecture. If you have any questions, now is the time to ask, but we can stop the movie. Time is up. Next time we're going to have the discussion. Yes?
You mentioned that we can make the multi-layer surfactant films on solid surface.
Right.
But how can you make head-to-tail contact between surfactants?
Well, if you take them up and down, it will be head to head and tail to tail.
Yes.
Now imagine, however, that you put them through the water, then take them from the other side where you don't have surfactant, and then dip them again. If you do it like that, it's going to be head to tail, tail to head. Now, if you put it like that, however, if you cycle it, surfactant, water out, surfactant again, water out, it's going to assemble the other way. It's not going. You're not going to take a layer on the way out. You're going to take another layer on the way in, and it's going to be reversed.
Why does the hydrophobic head assemble on the hydrophobic?
Because it doesn't have much choice. It's compressed into a crystal, and you just press it down. So where it's going to go? I mean, it just doesn't have a choice.
How
Yeah.
stable are these over time? Then?
This is a good question. And actually, the stability can be quite good. The real problem is, do they have defects or not when it comes to molecular electronics and high technology applications? And the truth is that there are defects, and these defects are very problematic.
Isn't it going to follow the corrugation of the surface or the structure?
Well, it's going to follow the corrugation, but you have a layer which is only 1/4 few nanometers thick. Then even the smallest defect on that scale is a mountain. So you can't expect to cover a mountain with this thin layer, and then you have problems. This is the reason why it's still not used in electronic devices, for example. People have been trying this for many years already. It's hard to do. It has defects. And then you can have just a single molecule of impurity, which, unlike the other molecules, would turn itself around. And I mean, you have a problem, obviously. So it's not easy, but in some cases it works beautifully. For lubrication, you don't care. I mean, it's just a molecular layer. Okay, so let's close officially. I don't know why the camera is still running, but let's close officially. If you have questions, drop by. I'll be here. Okay. It has to be smooth. It has to be smooth.